Stand under a big transmission line and look up. The conductors hang far apart, and each phase may even be a bundle of several wires. None of that spacing was chosen for looks. So here is the question. How does the simple shape of bare wires in the air decide the voltage hundreds of kilometers down the line? Because a real line is not a perfect wire. Along every meter, it carries three hidden properties: a resistance, an inductance, and a capacitance. Together, they set how much voltage survives the trip and how much power the line can carry. And remarkably, all three come from the geometry: how thick the conductors are and how far apart they hang. Start with the simplest one, resistance. Every conductor resists the flow of current a little and turns some of the power into heat. That is the line's loss. For alternating current, there is a twist. The current does not fill the conductor evenly. It crowds toward the outer surface. We call this the skin effect. It leaves the center barely used, so the effective resistance rises. Even so, on a high-voltage line, the resistance is small. It matters for efficiency and heating, but it is not what limits the power. For that, we turn to the magnetic field. Here is the big one. Any current wraps itself in a magnetic field, and that field stores energy. So the line has inductance, its opposition to a changing current. Now, here is the elegant part. The inductance of a whole three-phase line depends on the layout through just two numbers. The first is the geometric mean radius, or GMR. It captures the size of the conductor and its own internal field. The second is the geometric mean distance, or GMD. It is the average spacing between the phases. The inductance grows with the logarithm of GMD divided by GMR. In plain terms, spread the phases farther apart, and the inductance goes up. Make the conductor effectively fatter, and it goes down. This inductance sets the line's series reactance, and that reactance is what really limits how much power the line can push. Now, the mirror image. Two conductors at different voltages, separated by air, form a capacitor. So the line also has capacitance. Where inductance came from the magnetic field of the current, capacitance comes from the electric field of the voltage. Its formula has the very same shape. It depends on the logarithm of the spacing divided by the conductor radius. This capacitance draws a small charging current, even when nothing is connected at the far end. On long lines, that charging current becomes important. It can actually make the voltage rise toward the open end, an effect worth watching. Look closely at an extra high voltage line, and each phase is not one conductor but 2, 3, or 4, held apart by spacers. Why? It comes straight back to the geometry. Splitting one conductor into a bundle raises the effective GMR sharply, and a larger GMR means less inductance and a bit more capacitance. It also spreads out the electric field at the surface, which quiets the hiss and radio noise we call corona. The result is a line that carries more power, more efficiently. As the engineers say, geometry is destiny. Let's put numbers on it. Take a three-phase line on a flat tower. The spacings between conductors are 4, 4, and 8 meters. First, the geometric mean distance. It is the cube root of the three spacings multiplied together. That comes out to about 5 meters. Each conductor has a geometric mean radius of 1 centimeter, that is 0.01 meters. Now, here is a good place to pause. With a GMD of 5 meters and a GMR of 0.01, find the inductance per kilometer. Take a moment. Here is the answer. The inductance is about 1.24 millihenries per kilometer. At 60 Hz, that is a series reactance of about 0.47 ohms per kilometer. Multiply by the line's length, and you have the reactance that governs its power flow. Finally, put the inductance and capacitance together. Their ratio gives the surge impedance, the characteristic impedance of the line. For a typical overhead line, it is a few hundred ohms. And it leads to one beautiful number, the surge impedance loading, or SIL. It is the rated voltage squared divided by the surge impedance. The SIL is the line's natural loading, loaded exactly at its SIL, and the voltage stays flat from end to end. Below the SIL, the line's capacitance wins, and the voltage tends to rise. Above it, the inductance wins, and the voltage sags. So the same geometry that set the resistance, inductance, and capacitance also sets how much power the line most wants to carry. So, the parameters of a transmission line. Resistance turns a little power into heat, raised by the skin effect. Inductance comes from the magnetic field, set by the GMD and the GMR, and it gives the line its reactance. Capacitance comes from the electric field and draws a charging current. Bundle the conductors, and you raise the GMR, lowering the reactance and taming corona. Put inductance and capacitance together, and you get the surge impedance and the natural loading, the SIL. Every one of these came from a single thing, the geometry of the conductors in the air. Next time, we take these parameters and build the full line model. If this made it click, please subscribe, and I will see you in the next one.